Hey, welcome. Today, we're going to break down one of the biggest, most fundamental rules in the entire universe. And don't worry, we're not going to do it in some complicated lab. Nah, we're going to do it by following the simple story of a skateboarder on a ramp. Let's dive in. So, let me ask you this. What does a skateboarder just flying along have in common with a plain old apple just hanging from a tree? I know, it sounds like the beginning of a weird joke, right? But the answer is actually really simple. They both have energy. It's just in a different form. And that's the big idea we're going to unpack today. All right, first things first. Let's talk about the most obvious kind of energy out there. The energy you can literally see and feel. The energy of that skateboarder whizzing by at the bottom of the ramp. We're talking about the energy of motion. And here's the thing. It's that simple. From a huge planet orbiting the sun to a tiny little bug buzzing past your head, if it's moving, it has this energy. It's just a universal fact of life for anything in motion. And of course, physicists have a name for it. They call it kinetic energy. That word, kinetic, it comes from an old Greek word, kinesis, which just means motion. So yeah, it's literally motion energy. Simple as that. Now, how do we actually measure it? Well, there's a formula, but don't let the letters scare you off. Just think of it like a recipe. It's telling us exactly what ingredients we need to figure out the motion energy of pretty much anything. So, let's break it down. The first ingredient is m, and that stands for mass, which is basically just how much stuff something is made of. You know, how heavy it is. For our skater, it's their own weight plus the weight of their board. The more mass you have, the more kinetic energy you can build up. And the second ingredient is V for velocity, which, let's be honest, is pretty much just speed, right? How fast is all that stuff moving? The faster our skateboarder is going, the more kinetic energy they've got. But it's not quite a one-to-one thing. And this is where it gets really interesting. See that tiny little 2 in the formula? The velocity is squared. And that little 2, it's like a superpower. It means that speed is way more important than mass in this recipe. Think about it. If you double the skateboarder's mass, you double their kinetic energy. Okay, fine. But if you double their speed, you quadruple their kinetic energy. It has a huge, huge impact. So we've talked all about the energy of movement. But what about those moments of, well, stillness? What's happening when our skateboarder gets to the very top of the ramp and just hangs there for a second? I mean, really think about that. For just a split second, their velocity is 0, which, according to our recipe, means their kinetic energy has to be 0 too. But that energy couldn't have just vanished into thin air, could it? So where did it go?
It didn't vanish. It just changed costumes. It transformed into something we call gravitational potential energy. This is basically stored up energy. The energy an object has just because of where it is. The higher up our skateboarder is, the more of this weighting energy they've got, all ready to be used.
And the change in this potential energy all comes down to its mass, the pull of gravity, and this is the really important part, the change in its height. You lift something up, you're packing it with potential energy. You let it fall, and that energy starts turning into something else. So now we have these two types of energy, right? The moving kind and the weighting kind, kinetic and potential. And they aren't separate things at all. They're actually in this constant, really cool dance together, a non-stop trade-off. And you can see this dance perfectly if you look at the two extremes. At the very top of the ramp, the skateboarder is completely still. They have the maximum amount of potential energy, all that stored up height, but 0 kinetic energy. Then, at the very bottom, they're going as fast as they can. They've got 0 potential energy because they can't go any lower, and the maximum amount of kinetic energy. So the entire ride is just this beautiful, continuous flow. As the skater rolls down the ramp, they're basically cashing in their potential energy and turning it into the kinetic energy of speed. And then, as they roll up the other side, they use that speed, that kinetic energy, to buy back potential energy, climbing higher and higher until it's all gone, and they pause at the top, ready to do it all over again. Now, this elegant back and forth, this exchange, it's not random. It's actually governed by one of the most fundamental laws in all of science. It's energy's one single, unbreakable rule. I'm sure you've probably heard this before. It's the principle of the conservation of energy. And it just means that the universe is basically a closed system. You can't just make new energy out of nothing, and you can't make it disappear either. All you can do is change it from one type to another. So what that means is the total amount of energy our skateboarder has, their potential energy plus their kinetic energy, that total amount never ever changes. It's kind of like having a bank account with a fixed amount of cash. You can move money from your savings account, that's potential energy, into your checking account, kinetic energy, and back again. but the total balance always stays exactly the same. Okay, this all makes sense, but it leads to a pretty obvious question. If the total energy is always the same, why doesn't the skateboarder just keep rolling back and forth on the ramp forever? Let's follow the flow and see where it all really goes. In a perfect physics problem, on a perfect ramp with no friction, they would go forever. But our world isn't perfect, is it? We've got things like friction from the wheels on the ramp. We've got air resistance. So the energy isn't being destroyed, but where is it going? Well, to answer that, physicists have this really clever tool called a Sankey diagram. You can think of it like an energy map. It shows you exactly how much of your starting energy goes into the useful work you actually want, like motion, and how much of it gets siphoned off into other forms, which we usually call wasted energy. So for our skateboarder, a Sankey diagram might look something like this. Out of all the potential energy they started with at the top, maybe 85% of it gets turned into useful kinetic energy. That's the motion. But maybe 10% gets lost as heat, from the friction of the wheels. And another 5% gets lost as sound energy, that rumble you hear. But look, the totals still add up to 100%. All the energy is accounted for.
So that lost energy, it didn't really vanish. It just transformed into forms that weren't very useful for the skateboarder's motion. It became a little bit of heat and a little bit of sound. The unbreakable rule still holds true, even here in our messy real world.
Which, leaves us with one final and much, much bigger question. If all the energy that's ever existed in the universe is just constantly changing forms, where did that original stash of energy come from? Well, that's a question that takes us from a local skate park all the way back to the very beginning of time. Something to think about. Thanks for tuning in.